Did everybody catch on to all of that? Now, this circuit and what we're going to do is going to be a little bit of a lie, and it's intentional. But I want you to do what you think would work out. So I'll say it again. We're going to close switch A, that is time equals 0. And then I want you to find the instantaneous current in the bottom resistor, and then the long-term current in the bottom resistor. In the circuit, switch A is closed at time equals 0. I want the instantaneous current through the 12 ohm resistor and then the long-term steady state current through the 12 ohm resistor. Okay, give it a try. See what you can knock out here. These are pretty straightforward. They're not terrible. And again, just to time equals 0, it gave us a current of 3/2 amps. Oops, not 3/8, 3/2 amps. And then T infinity, the current was 8/5 amps. At infinity, remember, you treat this like it has 0 resistance. So it's the 12 and the 4 in parallel. Reduce that first, and then add it to the 12, and it's 24 divided by that. Pretty straightforward, I think. So these aren't terrible. And again, a lot like the capacitor ones. Here's what I want to really take a look at today. And I'm going to write this circuit out because I want you to see it that it can be done 2 different ways. This is the first way you can see this circuit with something we talked about yesterday called a make before break switch. A make before break switch allows you to make a new connection before the old connection is broken. So this is one way to build this circuit. And I'm intentionally leaving out a resistor, even though that's not particularly realistic because the wires would then become the resistance. The other version of this circuit, and they serve the same goal. And there's a way to make this circuit with just one switch, but I'm doing it this way on purpose, kind of. So in the circuit, oops. Need another switch here just to make it clear. There. In both of these circuits, you can isolate either the capacitor and the inductor with the EMF. So in the circuit on the left, if I want to isolate the inductor, I leave this switch in open position, and I move the make before break switch to the A position. This would allow me to charge up the inductor on its own. On the right circuit, I close switch A, leave switch B open. That isolates the capacitor with the EMF, and that would charge the capacitor up. On the make before break side, I can slide my make before break switch from A to B right after I close switch A. That means that I am removing the EMF from the circuit and beginning a circuit where all of the energy is in the inductor. On the capacitor side, it's easier to do this because the timing doesn't have to be special. I can open switch A and then close switch B. When I do that, I have all the energy in the capacitor, and then I close switch B, which allows the energy in the capacitor to be passed to the inductor. Regardless of which one of these 2 circuits we look at, what I want you to understand is the energy in a circuit like this can transition from the capacitor to the inductor and back. We're going to use this as our circuit because it's just easier to understand. And I want to start by saying we close switch A and let the circuit come up to a full charge condition, which means that after a long period of time of switch A being closed, our capacitor becomes fully charged. So we reach the state where the charge on the capacitor is going to be C times the EMF. This is at steady state. I'm intentionally using an uppercase Q to represent the maximum charge on the capacitor. All good? Any question about that? Good. So we can then, the capacitor is fully charged. I close switch B, and we have a Kirchhoff loop in here. In our Kirchhoff loop, we'll have the voltage drop across the capacitor and the voltage drop across the inductor equals 0. Now, if we're looking at the state of this problem, the voltage drop across the capacitor is going to be based on the charge of the capacitor. But do you realize the charge in the capacitor is not going to stay a fixed value for very long? The charges are going to attempt to equalize, and they have the possibility of running through the inductor when they do. But the inductor is going to present a back EMF, which is going to hold the charges in place instantaneously and then allow them to start moving through the circuit, increasing their current over a period of time until we reach a point of maximum current in the circuit. During that time, all of the energy will be switched over to the inductor. But then the inductor is going to begin to collapse, and the magnetic field is going to push those charges onto the capacitor until all of the charges have switched sides, and now the capacitor is fully charged. This is a simple harmonic oscillator, and the energy will oscillate back and forth between the capacitor and the inductor. You have the capabilities to solve this problem, but it's probably at the top end of your capabilities. So let's take a look and see what this would look like as a differential equation. And for you guys who have had mechanics, this should appear familiar. For you guys who haven't had mechanics or in mechanics right now, we won't see this until, well, April at the rate we're going. So the capacitor, negative Q over C. I used the lowercase q to indicate this is Q as a function of time, minus my inductor, which is defined as L di dt, which equals 0. Now, di dt is based on the rate of change of current, but current is its own differential. It's dq dt. So I want to get this all in the terms of a single variable, so I'm going to get the whole thing in terms of q. That means I have negative q over c minus L times the derivative of q with respect to t. You've seen this before, I'm aware, right? How you're supposed to write a second derivative. Everybody in mechanics should know it because we did it last year, but if you haven't done this before, the symbology is a little bit weird because it's a second derivative. We square the d's, even though you're not really squaring them, and then we write the dt as dt squared. It's symbology. It's really the second derivative with respect to t. I indicated this to you guys last year, that derivatives with respect to t become cumbersome. So there is other notation for this. Another way of writing this is negative q over c minus L q double dot equals 0. Dot notation is a way of shorthand writing derivatives. Several colleges will expect that you already know dot notation. So if you've never seen it before, the dot specifically indicates a derivative with respect to t, not anything else, just time. So I know that my college expected that I knew it, and I did not. And I've talked to former students, and it's UF often expects this, UCF often expects that you know this notation. And many of the students that are going there from out of state will know the notation. I don't know that it's taught in AP Calc, though, is it? Okay. I'm not going to use the notation. I'll stick with this. I just want you guys to be capable. To analyze this, I want to isolate the second derivative. So let's get it by itself. And when we do, we'll get the second derivative of q with respect to t equals minus 1 over LC times q. My understanding is that you probably don't have a mathematical way of solving this. This is a second order differential equation. And unlike calculus, you can't split the derivative and take the integral because it's a derivative of the second order. Order is kind of like polynomials, where we talk about a second order polynomial means polynomial is x squared. An order for a differential equation is the order of the derivative. So no matter how deep your derivative is, you could have a third derivative with respect to time. That'd be a third order differential equation. This is a second order differential equation. And what you have to start thinking about is that a differential equation tells you how two different relationships are related. That's what a differential equation does. In fact, this one says something very specific. It says, if I have a function, q, that is related to time, when I take the derivative twice, I get the original function back times a constant and a negative sign. That's how you read this. So you already know that there are functions that when you take the derivative, you get the original function back. Name one. So I know if my function was e to the, you say x, but we're doing t here. So I'm going to say e to the ct. This function, when I take the first derivative, dq dt, I get a constant and I get the original function, right? If I take the second derivative, the constant comes out again, I still get the original function. This seems like it fits. My second derivative produces the original function times a constant. It doesn't fit though. Why? The negative sign. Can that be fixed by putting a negative sign here? If I take the first derivative, I get the negative sign out the first time. But when I take the second derivative, I get that negative sign again, making it positive. Still doesn't work. Now, this process that we're doing is just called guessing an answer. It's not ideal. There are better things. But if you break out the old differential equation book, chapter 1, guessing an answer. And then the rest of the book is about what happens when you can't guess an answer. So that's what differential equations is about. There are methods here. You'll learn tons of them. But obviously, guessing is probably an inefficient way to do it. But you probably know a function that will work here. Go ahead. Sine or cosine would work, right? We know we take the second derivative of sine, we will get sine back, right? If we get the second derivative of cosine, we get cosine back. And in both cases, we'll get a negative sign during one of those derivatives. So sine or cosine will work. There is a better choice. Which one is better for us to use here, sine or cosine? Okay, I know you all said sine, but this is about charge on the capacitor. Is the capacitor fully charged at time 0, or does the capacitor have 0 charge at time 0? So without a phase shift, which function is at maximum at 0, and which function is at 0 at 0? Cosine would be a better choice here, rather than sine. So we ended up right here, and yes, we successfully came up with a function that we could use for Q that would be able to fit the parameters that are here. And do you remember why we would choose cosine over sine? Not exactly. We know that in both cases. I have two possible functions that we could choose. We could choose Q equals, and we got to put something here, and I don't know if you know what would go here, but it would be sine something times t. That's one possible function. The other possible function is Q something here, cosine c times t. These are the two possible functions that will work. Now, if we test them, and I'm doing this on purpose, but you need to pay attention, something needs to go here. Do you know what would go here? If you're truly understanding what these equations are all about, you should know what goes there. I indicated at the very beginning of the problem, but this is the charge on the capacitor. Yep. Q max, that's what should go there. We know that the charge on the capacitor is going to always never exceed a certain value. That value is going to be Q max. And we said that Q max was capital Q. That was from the very beginning. This is the boundary condition. At maximum, Q has to be at Q max. The first derivative for this function will produce QC cosine CT. And for this function, we'll produce negative QC cosine, I'm sorry, it's not cosine, sine CT. And that would be the first derivative. I know I said I wouldn't use dot notation, but I forgot to write dq dt, so I'll put the dot there. The next derivative, this will get its negative sign. So both of these are acceptable answers. They are solutions to the problem. There's still work to be done here, like what does C actually represent here? But before I get to that part, I could choose to use either one of these functions. Q sine CT is the original function here. So that's just what Q was, the original function. Q cosine CT, well, that's the function that's located right here. So if I reorganize this, I get negative C squared Q cosine CT. And if I reorganize this one, I get negative C squared Q sine CT. And hopefully see, this is this, right? I take the second derivative, I get back the original function plus a negative sign plus a constant. So this function works. Again, guessing a solution, not optimal. There are other ways to do differential equations, and guessing is probably not the best way to go. But even now, one of these is a better answer than the other. And we talked about why one would be better than the other. It's cosine. Cosine's a better answer than sine, because cosine at time 0 is at maximum. And we know our capacitor was at maximum at time 0. Now, you can use sine, but you understand that if you're going to use sine, you have to do something to the sine to make it fit your answer. And this is often what people would show as the answer. Right? Sine would fit both, but you'd have to put in a phase shift. How many of you remember phase shifts? That's not very many hands. So can we all agree that just choosing cosine might be better than using a phase shift? If not, do you know what a phase shift is? Oh my word, you don't know? It takes the whole function and shifts it one way or the other. The question here, let's ask this question. Let's see if you remember. If the phase shift is positive, does it move the function towards the negative side or towards the positive side? Yeah, it does the reverse, right? And if it's negative, it moves it towards the positive side. These are just, they're things you're supposed to remember. I don't care that you do. You'll never need it on my test. But again, I think it's nice that you remember things. This is our answer. Now, we're not quite done yet. This is close to the answer. But we need to replace C. What would we replace C with? You can't see it? It's right there in front of you. Do you have an answer, Miga? I'm a little sad, but that's okay. In this equation, do you know where the C squared is? 1 over LC is C squared. That's exactly right. So C is the square root of 1 over LC. Now we're going to do more than just this, but this is a lot already. So let's Let's get rid of this one because we're not using this one. And let's focus on our solution for just a minute because I don't need any of this anymore. That was just to prove that our function fits our pattern. And let's look at our answer. This is our answer. This is Q as a function of time for our circuit, and it's focused just on the capacitor. C here, we have set equal to the square root of 1 over LC to fit our pattern, that when we get our second derivative, we get C squared as the constant that pops out. So the truth is we could rewrite this function in better terms. We could write it as Q cosine times 1 over LC times T. This is a better representation of our function. You guys who have had Physics 1 or mechanics should recognize this as the functional equivalent to a harmonic oscillator. If you remember anything from that discussion, you should know that there's other things at foot here. And I want to make you smart people, but you tend to miss some of the details. So first, do we understand that the charge in the capacitor builds up in a positive direction, then builds back down to 0, builds up in a negative direction, then builds back up to 0? It's happening over and over again, right? We also know that the current in the rest of the circuit is the first derivative here. Right? This has to be the current in the circuit. Right, it's the first derivative. And there's no current in the capacitor, but the rest of the circuit would have to see this. Now, I don't want to leave here, but I want you to think about something, if you're capable. What must the units of this be? Perfect. Has to be radians per second. All right, when we take the trig, we take the sine or cosine, it has to be of an angle. We know that in nature, that angle's in radians. So this term really is what we call omega, the angular frequency. Right? It's going to be in radians per second. Now, keep this in mind. I believe that you guys are smart people, so it took a lot to get that, and I appreciate Vicki working that out for us. But let's go a few steps further. We know omega is used as a frequency measurement. It's the angular frequency. It's also used as angular velocity, but it's still a radians per second measurement. Omega, being in radians per second, could be converted to oscillations per second. Do you know how to convert from radians to oscillations? It's going to be a 2 pi conversion, correct? Do you guys, does this all ringing a bell to you at all? So there are 2 pi radians in every 1 oscillation. So if this is in radians per second, then the frequency would be the angular frequency divided by 2 pi. And this would be in units of hertz, right? Oscillations per second. Period is the time it takes for 1 oscillation. So period is the inverse of frequency. And this would be in seconds. So these two things represent how quickly our circuit oscillates in hertz. Now, I don't know if you're understanding why I'm being so deliberate here. but megahertz, kilohertz, gigahertz, are any of these terms you're familiar with? So your computer's oscillations per second is generally measured in gigahertz, right? Your current iPhone is running at what, 3.3 gigahertz is the current processor speed. The Intel i9, I think, is running at 3.7 gigahertz. It's the current Intel processor speed. That's how many oscillations per second. How do you create something in a circuit that can generate a frequency? This is how you do it. This is a tunable circuit where you can tune the frequency of the circuit. Right? We can determine what frequency we want the system to be tuned to. So if you want to say transmit in the FM range, FM is megahertz. Well, this is the key. A capacitor and an inductor tuned just right can force oscillations in the circuit. You put an antenna in the middle of this, and now you're running those electrons back and forth across the antenna at the desired frequency range. If you want to broadcast a message, your carrier signal would be that frequency. So right now, if you want to listen to, pick your radio. Does anybody listen to radio? I don't, but let's say you do. Layla, give me a radio station. 101.5 megahertz. So 101.5 times 10 to the 6 hertz. We could choose how we wanted to set up our oscillating system, because that has to equal omega over 2 pi, and omega is 1 over the square root of LC. Yep?
If it was a system like that, that's when it would be disconnected from the EMF, right? So if it's oscillating that fast, how is it not losing energy in the oscillations?
Very good question. Because what did we leave out of this circuit that has to be there? No. We intentionally left the EMF out. But we put the energy in the capacitor, and that energy is going back and forth between the capacitor and inductor. We've done nothing wrong there. But there is a fundamental flaw in our idea here. There's still resistance, right? So there is something in the circuit that we did not take into account. You guys are smart people. Can I show you why we didn't take it into account? Let's again say that we have a charged capacitor, and that at time 0, the charge on the capacitor is Q. All right? And right now it's charged. I have a switch here to maintain the charge in the capacitor. I have an inductor over here. But now, let's consider that there's resistance, even if it's a small amount, in the wires themselves. So I have a capacitor, an inductor, and a resistor. I take and close my switch at time 0. All good? Everybody following along? This creates a Kirchhoff loop through the circuit. That would be a voltage drop across the capacitor minus a voltage drop across the inductor minus a voltage drop across the resistor, which all has to equal 0. We continue to follow the same pattern we followed yesterday. We'll have negative Q over C for the voltage drop across the capacitor minus L di dt for the voltage drop across the inductor minus IR for the voltage drop across the resistor. All good? Let's put it all in terms of Q. So I have minus Q over C minus L di dt. Oops. We don't want di dt. We're going to put in ddt of dq dt minus dq dt times R. Let's maybe put this in rank order and, I don't know, get rid of all the negative signs. And I'll get the second derivative of q with respect to t with an L out front, plus the first derivative of q with respect to t with an R out front, minus plus q over c equals 0. This is also a second order differential equation. It's going to be a lot harder to guess at an answer, isn't it? Do you see why? You can try and guess at an answer, but it's going to be way complicated, isn't it? We can't split this derivative either. But this is a second order differential equation that has a first order differential in it as one of the terms. But you guys are smart. What do you think would happen to that energy? We've put the capacitor with the resistor by itself. What did that make for our Q as a function of T? What did it look like? Right, so if it was just a RC circuit, just going to put this off to the side for a minute and consider. If it was just an RC circuit, Q as a function of T was, right? This is one in which it's decaying because we don't have an EMF in there, so something like this, right? And how about the LR circuit? Do you remember what that one looked like? Now we couldn't use Q, but we used current, right? So current as a function of T was some maximum current, e to the minus LT over R. Now we know that when we have I'm trying to see how do I want to say this. If we have an LC circuit, we get Q equals just Q cosine T over LC. What do you think this circuit would probably have in it that it doesn't have now? It'd have decay. Would it still have oscillations? So it'd have oscillations that would slowly decay. Well, it seems to me that maybe we just smash these things together. Would that be the answer? Now, that's not proper math. There's problems with this. And you can probably imagine there's a few problems with this. Like, would it be this rate of decay or this rate of decay? I put in the rate of decay based on the capacitor because I'm just mashing things together. Now, we can't do the math, right? And to be honest with you, I would have derived it for you, but I ended up just looking it up. So, and hate me for it if you like, but you'll understand why I looked it up. Because here's what the actual answer comes out with if you use differential equations, and I couldn't remember my differential equations. But again, you'll forgive me. Write this big because there's a lot here. Right. Sorry. It's close to right. No. I just thought it'd be interesting.
It is.
There. Yeah. That's the actual oscillation and decay qualities of your circuit. And there's a lot of stuff to pick apart here. And already you've got your hand in the air, so you can just wait. It has components that you would expect, some of them. I obviously chose wrong, right? I probably should have put, it's the inductor part that's in the decay portion here, not the capacitor part. But I chose the capacitor part because it was the one that was Q and this one was I. That was it. I would have had to integrate to get Q from that expression. but also never would have predicted that the omega portion of the circuit would look like that. But that's the omega portion of the circuit. If we look at the omega portion, omega just by itself is, this is how it's expressed in this book, but 1 over LC minus R over 2L squared to the 1/2. Oh, I did that wrong there. There, squared to the 1/2. It's kind of weird, but the resistance plays a role in what the oscillating frequency is. It slows down the oscillations. Now, we know it plays a role in slowing down current because it did so in both the RL circuit and the RC circuit. But it changes the oscillating frequency of the circuit. Resistance is an adjustable thing. When you adjust, in the old days, there'd be a dial on your stereo to change the channel. You were adjusting a resistor that changed the oscillating frequency of the circuit. It was easier to adjust a resistor because they're easy to build. It's hard to make adjustable capacitors or adjustable inductors. So you tuned a resistor, which changed the oscillating frequency of the circuit. In similar way, that's still how we tune today, except we allow for electronic tuning. And what electronic tuning does is it does this in software by optimizing the highest resonant rate of the closest frequency it's trying to tune. So you might think you're tuning in 101.5, because that's what the dial said. But inside the black box in your computer, it's comparing 101.54 and 101.53 and 101.56 and 101.57, finding the optimum resonant frequency and locking into that frequency and doing that in software as opposed to doing it in hardware. You, in the old days, would just move the dial a little bit one way or the other. Because you drove around the city, some places had more reflections than the other, and the frequencies would be slightly different around the city for the same radio station. Also, have you noticed